Okay, thank you, Paul, for the introduction. And good afternoon to everybody who's joined to learn a little bit about bioplastics. So my name is Trevor HUTLEY. I'm a polymer scientist, technologist, and engineer. I studied polymer science and technology at Brunel University, and you'll see that that will appear as part of the story today. So I've worked around the world in the polymer and plastics industry. I've been an independent consultant for more than 20 years and member of the Plastics Consultancy Network. So let's start today. So you might think I'm still talking about automotive applications of plastics. Well, in a kind of way, bioplastics are materials derived from biomass, partly derived from biomass. And I just took this example of the Lotus Eco Elite because that central panel there is a thermoset plastic material containing hemp fibers. Of course, hemp is a bio-derived fiber. So in the definition, as we'll see later during this talk, of bioplastics, there is a percentage of the material which needs to come from biomass. It could be the matrix, or it could be the filler, or it could be the reinforcement. In this particular case, it's unusual because we're talking about thermoset materials and we're talking about fibers from hemp. So that's the subject of today, bioplastics. And what I want to cover today is a little bit about the past, the dynamic activity. There is a lot going on in bioplastics, and there's some insights into the potential future. So this year, bioplastics are about a $7 billion business, and 1 to 2% of the plastics produced in the world can be categorized as bioplastics, and we'll look at a number of those today. So this webinar will provide, I think, perhaps a different overview of bioplastics. I try to look at the very big picture. We look at some definitions and classifications, some historical insights and perspectives. As we go through, we'll talk about some of the drivers and the limits for the current activities, and then a scenario for the future potential of bioplastics. So that's the outline. First of all, a little bit of teaching. I put it in small letters here, polymer classification. It's part of my standard way of teaching about polymers, because I think it's important that everybody working in this area has got some clear definitions. Then we look at some brief history of bioplastics. We'll look at some definitions, and we'll look at degradable, biodegradable plastics, and part of the history of those materials. Some categories of bioplastics, one by one. We'll look at those briefly. We've only got half an hour today, and then some thoughts on the potential for bioplastics and some references you might want to study later on. So first of all, the teaching, classifications of polymers. This is what I typically teach about polymer materials to help people get their head around polymers and plastics materials. And I have developed over the years 8 classifications of polymers, and we're only going to look at 2 of those today. And first of all is about the source, the origin, where do polymers come from? And the second is the technological use, the industries that have grown up using polymers. So we'll just quickly pass over those so you've got the right framework and perhaps thinking in your head here. So classification 1 is about where do polymers come from? What is their source? What is their origin? And keeping it very simple, we could say, first of all, polymers come from natural sources or synthetic sources, or they're synthesized. So natural polymers, for example, cellulose, it's the most abundant polymer on the planet. About 60+ billion tons of cellulose are generated each year. And chitin, probably the second most abundant polymer, 10 billion tons per annum. Just to put it in perspective, and then the synthetic polymers, of course, there are dozens of them, but just take the common ones here. And the total plastics industry is about, these days, 0.38 billion tons, just to put it in perspective. So that's the classification. Where do they come from? Origin, source, natural or synthetic. Now, the polymer industries, it's quite interesting that a number of industries have grown up over the years based on polymers. For example, adhesives, fibers, elastomers, paints and coatings. The area we want to look at today is the area of plastics, and we can subdivide those, as we've already mentioned, into thermoset plastics and thermoplastics. So that's the area of focus today. So we're not going to look at those other areas where polymers are enormously consumed and used and bring amazing performance. But it's quite important that we get these categories clear in our minds. For example, one of the stories that many of us hear about microplastics. But when you look at microplastics, you find that 1/3 of them are fibers coming from clothes, so nothing to do with plastics, and another 1/3 are either tires wearing away or road markings, which is in the category of paint and coatings. So at least 70% of what are called microplastics, at least, are nothing to do with plastics at all. So it's very important that we get clarity in our minds of what these words mean. So that's the kind of teaching stuff, and now into the real subject itself. Now, when I started to look at bioplastics recently and started to collect together all the statements and words and comments and observations about them, I came across such an enormous selection of words and phrases that some of them were completely new to me, and I had to kind of find my way through this. And so that's it's quite surprising how complicated this whole topic is, and how many new words and phrases and loaded phrases there are in this area. And some of that we're going to try and look at today to try and understand what does it mean and what can we do about it. So it is a complex area. It's got its own terminology, it's got its own definitions. We're going to try and look at some of those. Now, this is a typical picture that you may see in the press these days. This is plastics on a beach in Norway. This is part of the story, the environment in which we're actually working as a plastics industry. So I think people are kind of almost asking this question: are bioplastics the solution to the pollution? And do we want to see a beach that's covered in plastics? Are bioplastics the solution to taking us back to great oceans and great beaches? This is part of the pressures that plastics are facing. Plastics are polluting the world and oceans. How many times have we read that and seen that? Fortunately, there's one person, Dr. Chris de Armit, who's spent a lot of his time and effort into collecting together the facts and information on this story. And if you haven't seen this book, which I'm putting right in front of my face, so I guess you can see it now, or looked at his website, plasticsparadox.com, you really ought to, because this is an amazing collection of facts and explanation of the reality of what's happening around us. I won't spend any more time on it, but it's really worth studying and reading in detail. And actually, his book is now available for free online. I mean, I bought it through Amazon like we usually do. So the second part of the pressure that plastics are facing is a kind of a sentiment against what's called fossil fuels. And that happens within an ambience that views carbon dioxide as a pollutant and seeks to minimize carbon in a drive to net zero. None of this is a story that I subscribe to at all, but that's the environment in which we have to work in the plastics industry. And some of the feeling about bioplastics, I think, is that bioplastics are like the answer to those polymers based on fossil fuels, fossil sources. So bioplastics is seen like the good guys versus the fossil polymers. And the use of the word bioplastics kind of suggests, the way it's used, the word itself suggests that any polymer derived from biomass is environmentally friendly. Well, that may not be the case. That's kind of the situation that we find ourselves in the plastics industry, and into which bioplastics is being very active. Now, many of these stories that we see, like the pictures of the beach and that, there are things that we can do something about. We can all reduce plastic waste. We can eliminate plastic litter ourselves. Maybe we can't do that everywhere ourselves in the world, but we can all do something about it. So no more about that story. I just wanted to give the perspective. Now, as we said in the introductory slide, about 1% of the plastics produced in 2022 in the world would be categorized as bioplastics. That's down from 100% in 1862. That might be a surprising statement to some people. 1862, well, what happened in 1862? Well, that's when the first man-made plastic material, Parkersine, was shown at the London International Exhibition in 1862. Sorry, typo here. His patent was issued a few years later. British Patent 1313 issued a few years later, 1865. So bioplastics started at that time, in a sense, because Parkersine was a plasticized cellulose nitrate based on cellulose. And we'll see in the next slide, many products were made using this kind of a material. And this was kind of the beginning of the plastics industry. Now I've got a slide, an old slide here that I'm continuously updating about how the world plastics production has increased. It started in 1950, my graph, because that's when we exceeded 1 million tons. Of course, in the time of Alexander Parkes, he started in the kilogram quantities. So that's the perspective. We started off, first man-made plastic was based on cellulose. Now, cellulose is a highly crystalline material, so it's not processable by thermal methods, and decomposes before it melts. But if you nitrate it or carry out other chemical processes on it, you can begin to use it as a material and make it processable. So that's where it all started. 1862, 100% of the materials were bioplastics. And some of the parts that he made and exhibited at that exhibition in 1862. So cellulose, as we said already, it's the most abundant polymer, at least 60 billion tons per year, and it varies across the plant kingdom. Now, in wood, for example, you also find lignin. This is, in a sense, the second most abundant natural polymer. It's an aromatic biomacro molecule, and it's extremely complicated. This actually is a very good representation of kind of the phenolic structures, and it could be a source for bio-based materials. Indeed, it is already beginning to be used in that way. So there are natural materials available. Cellulose-based plastics have also been developed since 1920, so about 100 years ago. For example, cellulose acetate, cellulose acetate propionate, cellulose acetate butyrate. So these cellulose esters have been around for 100 years. They're still made, they still have their own niche applications as materials, all bioplastics. We could also say that this year, about 0.25% of the polyethylene produced in the world will be categorized as biopolyethylene. And that's down from 100% in 1933. Again, what's the background to this? Well, Fawcett and Gibson in ICI research accidentally polymerized ethylene and made what became polyethylene and became low density polyethylene. But this polyethylene was made from ethylene that was made by dehydrating ethanol produced by the fermentation of molasses. So bio-sourced ethylene was the basis of the polyethylene industry from the beginning in 1933. And that industry has grown in 80 plus years to become around 100 million ton business, and now starting to look again into the bio-sourced monomers. I've used this word here, as German word really, plastic optimismus, because this was the kind of the feeling that there was. It's a description of how people were thinking and feeling about plastics materials in this kind of a time frame. In the earlier parts of last century, we're looking at the possibilities and future of plastics. We'll come back to that word perhaps a bit later. So bioplastics then and now. How did we go from 100% bioplastics to maybe 1%? How do we explain this historical development? I think it's this tension between carbohydrate and hydrocarbon. And from the time of World War II, the increasing availability of hydrocarbon resources, oil and natural gas basically, and the development of chemical reactions and chemical engineering processes on an ever increasing scale led to an economic base for plastics production that could not be matched by carbohydrate based polymer industry. Now, where we are now, where we are clearly at the hydrocarbon end of the spectrum, of course, the oil price, as we've seen ourselves in the last few years, and in fact in the last decades, is a very, very volatile number. And that, of course, affects the attractiveness of alternatives, such as carbohydrate or bio-based polymers. Some definitions related to bioplastics. Biocompatible, we sometimes say. Well, this is a polymer that's not harmful to living tissue. Polymers are used in our bodies by medical professionals. A biopolymer is a polymer of natural origin. We talked about this already. But a bio-derived plastic is a plastic material partly derived from biological sources. A bio-sourced plastic is a plastics material partly derived from biological sources, slightly different emphasis in terminology. A bio-based plastic is a plastic material based on biological sources. A biogenic plastic is a plastic material made directly by a biological agent, such as bacteria. And all of these definitions have somehow all come together and become part of the terminology bioplastic. So at this stage in our discussion, a bioplastic is a plastic material derived, partly derived, wholly derived from biological sources. And the most recent way of thinking about this is to look at renewable biological sources. Some people write about annually renewable biological sources. So the next part of the definition that we need to think about, because this is the other side of bioplastics, is to look at degradation and biodegradation. So hydrolytic, oxidative and photodegradation of plastics is well known and understood. It's a definition of them. But biodegradation of a polymer or a plastic is a combination of these abiotic, non-biological reactions, which we've just listed here, plus the cleavage of the polymer chains by enzymes. And then this is turned into the metabolic products of the microorganism that's present, the bacteria, the fungus, the algae that's generated those enzymes. And this biodegradation is a function of pH, temperature, moisture content, oxygen, nutrients, and some understanding of the stages of biodegradation. So it's quite important to understand that biodegradation is a process that happens to plastics materials. Now, composting is a process for treating waste materials, and we end up with a definition of a plastic or other material that is compostable, and they must decompose by 90% and mineralize within 3 months. In an industrial composter, and we don't have too many of them around yet, but in an industrial composter between 50 and 60 degrees Celsius. And we start to get into some of the tension here. Biodegradable is not always compostable, and compostable may be biodegradable. There's still, I think the jury is still out on some of these statements and definitions. What I wanted to look at quickly was my own kind of first involvement with bioplastics, which was when I was at Brunel University in the early 70s. And Jerry Griffin was the reader in polymer science, and he had a project with Colorado to develop paper-like plastic materials, low-density polyethylene. Mineral fillers were found unsuitable, but a particulate starch in particles was found to be very effective. But this was at a time when already the plastics industry was under criticism as a growing source of pollution. So he started to look at the biodegradability of this low-density polyethylene starch formulation. And it was interesting that it was found, and actually we as students were even putting these bags into our gardens and seeing how they behaved in the soil. But it was found that they behaved differently with the municipal solid waste in the landfill. And it was found out that this was due to their contamination with cooking oil. So the formulation of what was called bioplastic at the time was reformulated to include a small amount of oleic ester of octanol with 7% starch. And it was found then that the damp soil contact introduced sufficient transition metal contamination to start oxidizing this fatty acid, unsaturated fatty acid, and then the chain breaking oxidation process began and the biodegradation continued. And then he later formulated this using a dyeing rubber instead of the fatty oil, and included specifically a transition metal salt because putting it in contact with soil was too variable. So I think it's quite interesting that in the 70s and 80s, a master batch containing a transition metal salt to impart controlled degradation was already out there, and this was maybe an idea ahead of its time. So biodegradable plastics, and that may have been the very first ever biodegradable plastic bag in the 70s. It takes us now to another stage of definition of bioplastics. We were at this stage, bioplastic material is derived from renewable biological sources, but now we add to that, in the current understanding, that not only is it derived from renewable biological sources, but it might also be a plastic material that biodegrades. So it could be one of those, a plastic material that biodegrades is a bioplastic. A bioplastic could be a material made from biological sources, or it could be both. So I found this not to be a very clear and helpful definition, even if it is the current accepted one. My view is that bioplastic should not refer to biodegradable plastics. We already have a definition and a statement and a category for those. My preferred definition would be just a bioplastic is a plastic material partly or wholly derived from renewable modern carbon biomass. I want to look quickly now at some of these classifications. we're quite used to hydrocarbon derived plastics, and many of those, of course, we know these materials, not biodegradable. But one or two hydrocarbon derived plastics are biodegradable, a few. Polycaprolactone, polybutylene adipate terephthalate, and polybutylene succinate. Then we can add another dimension to this story here and say, well, what about the bio-derived or carbohydrate-derived materials? And actually, there's suddenly now a whole group of these materials which are potentially derived from biomass. Some of them are different materials to what we had before, and some of them are the same materials, exactly the same, but using partly or wholly bio-sourced monomers. And then we have another category now, bio-derived polymers that are biodegradable. Thermoplastic starch, polyhydroxyalkanoates, and polylactic acid. And we'll try and look at some of these. I can see the time is running away, so we may go very quickly through those. But what we can learn from this kind of classification is that bio-derived does not mean biodegradable. Biodegradable does not mean bio-derived. And these are easily confused, and this is where some of the marketing and labeling confusion arises. And actually, the Federal Trade Commission have put out a huge paper, and the reference is at the end there, explaining what some people say and what they really ought to say. Some of it's confusion, some of it's deception, some of it's misunderstanding statements. Some of them are very unclear, greener than our previous packaging. Lots of statements about products that are causing confusion in the marketplace. There's a lot of opportunity to improve. And there are a lot of eco labels. Now, 455, they're all collected in one place. And some of these are reasonably clear as to what they mean. And some of them we need to learn about. There are a lot, I can tell you. And let's just have a quick look at some examples of bioplastics. Thermoplastic starch, which is biodegradable, bio-based. I mean, all starch is bio-based, kind of by definition, and it's biodegradable, but it's usually blended with other polymers. Polycaprolactone, PCL, is not bio-based, but it's biocompatible and biodegradable. Polyethylene, as we saw, was bio-based, now it's mostly not, and now it's becoming a little bit bio-based. So it's changed. It's biocompatible, it's not really biodegradable. Polyhydroxyalkanoates, PHA, these are the biogenic polyesters. They're perhaps in a special category. These are actually polyesters that are made in the bacteria. We'll come to those in a moment. And polylactic acid, entirely bio-based and compostable. And a little bit here about PET, which has been classically based on hydrocarbons, now available from some suppliers in bio-based form. It's not biodegradable, but it's partly or totally bio-derived. From the point of view of time, we're going to be a bit tight on this, so we won't go through any of this in any detail. It'll be in the slides which you'll be sent. But perhaps look at this story about the PET bottles, because this is something I often use as an example in the history of plastics here, that Nathaniel Wyeth developed at DuPont biaxially oriented PET bottles. One of the senior scientists said you've got as much chance of producing that as balancing a steel ball on the end of a needle. But he persisted and he got the patent. And although DuPont never made the machinery or the polymer or the products, they received license fees for years and years on this product. And in 2009, Coca-Cola introduced the plant bottle, which was 30% plant-based. They used bioethylene glycol. And then last year, the plant bottle became 100% plant-based, because they have a process for developing plant-based terephthalic acid. Now, I think one good thing that Coca-Cola have done, they've shared their technology and they've made this available to other people. So that's PET, how that's changed. Polyhydroxyalkanoates, as I mentioned, they're accumulated by many bacteria to store carbon and energy, and the polymer can be extracted, not trivially, but can be extracted from the bacteria. And PHA is not a polymer, but it's kind of a family of polymers, of which over 150 have been identified so far. So this was maybe the first, P3HB. If you take that methyl group and change it to other groups, you get part of the whole family of materials. Back in '83, ICI, which used to be a big chemical company, they created the first bioplastics company, Marlboro Biopolymers, and their plastic was called Biopol. And it was a copolymer of this polymer here and a very similar polymer where the methyl group becomes an ethyl group. And this then became owned by a number of people all around the world, and was first used to make a shampoo bottle many years ago. And again, you have to look at this in your own time. We don't have time to look into that, but sometimes it's helpful to just have this kind of factual information kind of ready at hand for you. PLA is derived from a plant sugar by fermentation and then a ring opening polymerization to produce polylactic acid, which is a thermoplastic polyester, and it's now being made on significant scale, several quite large plants, 150 and 75,000 tons, and a third plant is going to open soon, I believe, a few years' time, again in Thailand, another 75,000 tons. And PLA has quite a few people active in this space, maybe two big ones. I've added Total Energies Corby onto the table here. They're very big in this story right now. So PLA is quite an important material for the bioplastics industry. There are a number of people active in what we could call the aromatic polyester space of biodegradable polyesters. Most of these are polybutylene adipate terephthalate copolymers. The Biomax from DuPont was polybutylene succinate terephthalate, but very similar polyester copolymers, and they had arrangements with Plantic to blend this for starch. Lots of stories connected with this. And then I thought this was quite an interesting product from the Japanese, from Mitsubishi. They've developed basically a polycarbonate analog using isosorbide in place of bisphenol A, and it produces a new material really that's somewhere between polycarbonate and acrylic, PMMA. And one of the earliest materials, Matabi, the now become a whole family of materials from Novamont, and BASF has been there since the very early days. So what is the current status? Because we need to come to a close quickly here. What is the current status 2021? This from the European Bioplastics Organization. They have these very helpful charts which summarize everything, showing the biodegradable and the bio-based non-degradable materials and their approximate percentage of the total production. 2.42 million tons last year, and this year perhaps maybe about twice that. So that's kind of the current status where we are. And what could it look like? I just wanted to read this for you. In the present contention with biotechnology, the economic pressure to build big and reduce costs will be irresistible. Indeed, if we're going to replace oil-based chemical products, our ability to build and operate large-scale plants is as important as it currently is for polyethylene. Part of this lies for the basis of the economies of scale of the chemical industry. That sounds like a very true and accurate statement, and actually it was said in 1982. So there were a lot of people thinking ahead on this topic a long time ago, the best part of 40 years ago. Now, of course, hydrocarbon polymers, they benefited from 60 years more of optimizing processes and products and polymerization and monomer and intermediate synthesis. So there's a long way to go because one industry has developed enormously. So what could that look like? So going back to what is driving plastics, these are the statements I normally make about the drivers for plastics. And I include that driver, carbohydrate versus hydrocarbon, but now I've put it in the category of drivers for the growth of bioplastics. Economies of scale we've just mentioned, and the regulatory. Of course, if you have to have 20–30% of bio-based material, it causes a big drive in that direction. So what could it look like? So going back to my ancient world plastics production, what about if I extrapolate that a little bit further forward, say to 2050? What could the plastics consumption of the world look like at that time? And where would the bioplastics fit in that story? Maybe coming along here, and this is my best estimate and calculation. Bioplastic optimismus, as I said, is that scenario where we have optimism and creativity for the future. And I think that kind of applies to the bioplastics industry now in a way that it did perhaps almost 100 years ago. So what have we seen? Bioplastics are the original plastics. We've seen some examples quickly of plastics since the 70s. The tension between hydrocarbon and carbohydrate. Further clarity is required on some of the drivers. And we have optimism and imagination for the future, and some references for you to study, acknowledgements to all the people who provided stuff on the web for me, and now we're at the Q&A. Be happy to answer any questions you may have.
Well, thank you very much, Trevor. That was really appreciated and incredibly insightful. We've had a few questions come in, but I would encourage the audience, if you do have any questions, there is still time for you to submit those. So to start with one,